In this video, we're going to consider the kinetic energy of a system of particles. What we're going to do is very similar to what we did in the last video, video number 19, where in there we were concerned with the angular momentum of a system of particles. So it's a very similar setup, obviously. Here we have a number of discrete particles here. We designate them as particle I, and our system of our, say, swarm of particles has a center of mass, and the center of mass has a position vector from point O, D, and then the position vector for any of the particles in the system from point O is Ri. Then, as you saw us do in the last video, from the center of mass, we can have a vector going out to any one of the particles in the system. So if we set it up like that, then this position vector Ri would be the sum of the position vector for the center of mass, D, plus Ri prime. So we have our position vector equals D plus Ri prime. And like you saw us do in the last video, we can take the time derivative of each side. This gives us the velocity of any one of the particles relative to point O. So for example, these might be a swarm, say, of celestial objects going past, and we're in a galaxy at position O, and we're measuring the velocity of these different celestial bodies. That's what VI would be then, and that will equal the derivative of this, and that's the velocity of the center of mass relative to our observer at point O, plus the time derivative of this vector, and that is the velocity of particle I, or of celestial object I, relative to the center of mass. So if we were, say, standing here at the center of mass, and we were measuring the velocity of the different particles or the different celestial objects in our system, that's what the VI prime designates. So, but if we're here, then the velocity that we measure, that is equal to the velocity of the center of mass plus the velocity of any of these particles as measured by an observer standing at the center of mass. Now, if we're concerned with the kinetic energy of the system, we're the observer, and we're measuring, we want to know the kinetic energy of this. Of course, the general formula is, or say just for one of these particles, it would be 1/2 mi vi squared. And if we add it up for all of the particles in the system, then that would be the total kinetic energy. Our general formula for it, anyway. Now this vi squared, that would be the dot product of vi dot vi, but vi is this. So we can say that vi squared will equal the dot product of this with itself. Like this. So let's go ahead and take this dot product and see what kind of an expression it gives us. So vi squared equals this dot this, that's the velocity squared of the center of mass, plus this dot this, that's the velocity squared of any particle relative to the center of mass. Then we also have the cross products, so that gives us, we'll write it like this, say 2 v dot vi prime. So there is vi squared. Here's our general formula for kinetic energy. So we can substitute this right here in our formula. And that's what we're going to do. First we're going to erase all this and make more space on the board. But what you're going to see then is we're going to use this to substitute for this in our general formula for the kinetic energy. So we have kinetic energy equals 1/2 summed over I, then we had mi vi squared, and vi squared is this expression, the velocity squared of the center of mass plus velocity squared for any particle about the center of mass plus this cross term. So we have three different terms that we're summing over, here, here, and here. Let's take them one at a time. Now notice this is the velocity squared of the center of mass. That of course is not summed over I, so we could just take this, put it to the outside of the formula. So from our first term we would have k equals v squared 1/2 sum over I mi. But this would just be the total mass of the system. So from the first term we have kinetic energy equals 1/2 mv squared. Capital M v squared. So of course that's the kinetic energy of the center of mass of the system. But we have more terms to consider. Here we have this term, so we're going to have plus 1/2 the sum over I mi vi prime squared. Now what does this term mean? Of course, vi prime, that is the velocity of any particle relative to the center of mass. We have vi prime squared multiplied by the mass of that particle. So this we can think of as the kinetic energy of the system relative to the center of mass of the system. So if we were right here at the center of mass and we were trying to measure the kinetic energy, that is what we would have. Now, we still have another term to consider though, this term. Here we have 2 times 1/2, that goes away. And here we have v, that is the velocity of the center of mass. That's not summed over I, so you can take that to the outside. So what we will have then is this expression plus, taking this to the outside, dot, sum over I, vi prime times mi from here, vi prime. And we're taking the dot product of this with the velocity of the center of mass. But what does this term mean? This is a momentum term, obviously, mass times velocity. This is the velocity, again, relative to the center of mass. So this is the momentum relative to the center of mass, adding it all the momentums up. So what this term represents is if we were here at the center of mass and we were adding up the momenta for all the particles that we have, sum them all up total, that's what this term is. But now remember, VI prime, that's the time derivative of Ri prime. Ri prime is the vector that goes from the center of mass to any one of these particles. So this term here, we can rewrite it like this, d dt. Then here we have Ri prime. But now, hopefully you remember from video number 19, our previous video, this summation is 0. So this term drops out. Before we erase it, we want to comment on it for a little bit, then get back to our kinetic energy. What this is telling us then is that if you're here and you add up the momenta for all the objects surrounding the center of mass, it comes out to 0. Now, in either the next video or the video after, what we're going to do is we're going to consider the trajectory of a solid particle. Then after that, consider the trajectory of the solid particle, the fragments of it. The solid particle blows up while it's still going through its trajectory. Understand how that works. We have to realize that, again, the momentum, the total momentum taken about the center of mass of any system adds up to 0. And again, this will be of particular significance in one or two more videos when we consider trajectories. But so this term here, though, for the kinetic energy, this is 0, so we can take this away. And here then is the expression for the kinetic energy. So this would be then, that's the kinetic energy of the center of mass of the system, plus this would be the kinetic energy relative to the center of mass of the system. Now, so for our system then, these particles, they have a translational motion and a rotational motion. If these particles here, these individual discrete particles, if together they comprise a solid, rigid object, then that solid object, when you throw it and give it a torque and it starts rotating, it always rotates about its center of mass. So taking that into consideration, what would be the final formula for the kinetic energy of a, not just a swarm of particles like we have here, but a collection of particles that together comprise a rigid body? Now, remember that when we have rotational motion, as we, I think it was in video number 16, for example, if we're going to say in a uniform circular motion, and here is an arc length S over an angle theta. Of course, that arc length equals the radius times the angle, provided the angle is measured in radians. And this arc length S, that's a linear distance. If we take the time derivatives, that the linear velocity equals r d theta dt, and that is the angular velocity, omega. So here, for this, VI prime, we can consider it like this. Now, VI prime is velocity relative to the center of mass. So it's the time derivative of Ri prime. What we can have then is that VI prime that is equal to its magnitude, Ri prime, times the angular velocity of the rotation. So this squared, we would have kinetic energy equals 1/2 mv squared plus 1/2 sum over I mi. Then we would have Ri prime squared omega squared. But this, hopefully you remember from our previous videos, that's the general expression for the moment of inertia. Specifically, remember what Ri prime is. It begins at the center of mass and goes to that particle I. So this is the moment of inertia with respect to the center of mass. So for a solid object, we have that the kinetic energy, a solid object that has translational and rotational motion, the kinetic energy has this formula, where the moment of inertia is taken about the center of mass of the object. So its total kinetic energy is equal to that from the linear motion, the mass of the system times the velocity squared, plus this is the kinetic energy then due to the rotation of the solid object. Okay, that's it then for this video. Again, to remind you, the playlist for all the videos is featured at the website digital-university.org.